So today, we're talking about a whole new way to build powerful AI. It's a technique that kind of moves beyond just throwing more and more computing power at a problem, and instead starts to look a lot more like, well, biology. We're going to get into how AI development might be shifting from the server farm to something that looks more like a breeding program.
Yeah, seriously, just think about that for a second. Forget training these massive models from scratch. What if you could just take two existing AIs, maybe one is a language genius and the other is amazing at math, and, combine their strengths to create an offspring that's just better than both of them? That's the wild idea we're diving into.
Okay, so this idea of mashing models together isn't totally new. It's a thing. It's called model merging. But as the researchers at Sakanai AI point out in their paper, right now it's pretty much a guessing game. It's all based on human intuition and a lot of trial and error. As they put it, it's basically alchemy, not science.
So you have to ask, why are people even bothering with this black art if it's so random? Well, the answer really gets to the heart of a huge economic problem in the world of artificial intelligence right now. Look, building a brand new foundation model, something like a GPT-4 or a Llama, is just outrageously expensive. We're talking mountains of data and entire data centers worth of computing power. It means that creating truly cutting-edge AI is pretty much impossible for anyone who isn't one of a handful of giant tech companies. And that's why model merging is so appealing. It's a much, much cheaper way to go. You can take models that are already out there, fuse them together, and hopefully create something new and powerful without any of that expensive training. But like we said, it's totally hit or miss. It feels like you're trying to find a magic recipe in the dark, and everything just depends on the gut feeling of the person doing the mixing. Okay, so this is where the real breakthrough happens. The researchers behind this paper basically asked, what if we could get the human guesswork out of the equation entirely? What if we could take a lesson from nature and turn this alchemy into a real automated science? And there it is. That's the big idea. Instead of a human trying to guess the perfect recipe for merging models, they decided to just let evolution figure it out. The plan was to automatically breed generations of AI models and let natural selection find the absolute best combinations all by itself. So for anyone who's not familiar, an evolutionary algorithm is pretty much what it sounds like. It's a computing method that's inspired by Darwin. You create a whole bunch of potential solutions, you test how fit they are at whatever you're trying to do, and then only the best ones survive to mix together and create the next generation. You just repeat that process, and over time, the whole population evolves toward the best possible answer. So to actually breed these AIs, the researchers came up with two totally different strategies. I love the way they think about it. One is like mixing different paint colors together, and the other is more like building with Lego blocks. Let's dig into how they work. Right, so here are the two paths. The first one, parameter space, or PS, is all about blending the internal knowledge, the weights of the models. That's the paint mixing analogy. The second one, data flow space, or DFS, is way more radical. It's about actually rebuilding the model structure, its architecture. That's the Lego block approach. So let's zoom in on that first method, parameter space. Here, the algorithm is basically trying to find the perfect recipe for blending the ingredients from the parent models. It tinkers with the mixing ratios for every single layer to create this new hybrid set of internal knowledge. And this visualizes it perfectly. You've got your parent models, the blue and the red ones. The parameter space approach blends their layers together, and what you get is a new purple model. It has the exact same structure as the parents, but what it knows on the inside is now a hybrid of both.
All right, now for the second method, this is where things get really interesting. With data flow space merging, the algorithm isn't blending anything. Instead, it takes the layers from the parent models, those Lego blocks, and it starts experimenting, stacking them in totally new and weird orders to create a kind of Franken model.
So to break that down, the process literally disassembles the parent AIs. It takes each layer as a building block, and then it just runs thousands of experiments, trying to find a new, better way to snap them all together. It's not searching for a new recipe, it's searching for a whole new architecture built from parts that are already trained. So all of this sounds cool in theory, but does it actually work in practice? Well, to prove it, the researchers set up this really clever challenge. They wanted to see if they could evolve an AI that could solve math problems, but specifically in Japanese. To do this, they started with 3 parent models. The first one was a really strong Japanese language model, but it was just awful at math. Then they took 2 powerful English language math models, but of course, they couldn't really understand Japanese. So the key thing here is that none of these models could do the final task on their own. And this just shows you how poorly they started out. On a Japanese math test, the Japanese model scored under 10%. The best English math model only hit 30%, and that was mostly because it just struggled to understand the questions in Japanese. So let's be clear, the starting point was really, really low. And this was the result. The best model that their evolutionary process spit out scored an incredible 55.2% accuracy. That is almost double the performance of the best parent model. It's a huge leap in skill, and remember, this was created completely automatically with absolutely no new training. But this slide shows something even crazier. This wasn't just about getting a better average score. If you look at those top 3 rows, those are the parent models. You see a lot of gaps, a lot of problems they just couldn't solve. But the bottom rows, the evolved models, they're way more filled in. They actually solved problems that none of their parents could handle alone. This is what you call a true emergent ability. I mean, the implications here are just massive. This isn't just about creating one cool model that can do Japanese math. This is about demonstrating a fundamentally new, more efficient, and incredibly powerful way to build AI in the first place. So let's just quickly recap what they pulled off here. They automated the alchemy of model merging and turned it into a science. They created a model with brand new skills, Japanese math, from parents who couldn't do it. They ended up with a model that could compete with others 10 times its size. And the craziest part, they did it all super efficiently with no expensive retraining. Let's actually look at that size comparison because that is the real jaw-dropper. Okay, this chart really puts it all into perspective. What you're seeing is their little 7 billion parameter evolved model, compared against other top-tier Japanese language models on general performance tests. And what's just wild is that their tiny model is performing right up there with models that are 10 times bigger. This is a huge, huge win for efficiency. It shows that a smarter combination can be way more powerful than just making things bigger. And that really brings us to the biggest takeaway of all. By letting an evolutionary algorithm loose to explore this massive space of possible combinations, we can actually discover new and totally unintuitive model designs that are more powerful and more efficient than anything a human expert might have come up with on their own. You know, this just opens up such a fascinating new door. We've gone from painstakingly crafting AI by hand to creating the conditions for AI to just evolve itself. And it leaves you with this one big question. If we just let this process run generation after generation, what kinds of new skills might pop up that we can't even begin to imagine today?